So once we have a vector functions or parametric equations, a curve, there are certain features that we would like to be able to compute that might help us understand the curve. So one of these quantities is an arc length. So let's talk about that in this video. Okay, so depending on the Calculus 2 class that you've taken, you might have seen a formula for arc length, or maybe you haven't. It's possibly an optional topic, but let me remind you what the formula looks like. So in Calculus 2, if you have a function, some function f of x, you can kind of look at the arc length as kind of sum of chain link created by breaking up the curve into lots of small line segments. How does that help us? Well, each line segment, you can kind of look at it as a right triangle. And maybe this length I'm going to call delta x. And then the height of this right triangle, maybe I'll call that dy dx times delta x. Well, this a little bit is the rise component. And dy dx is the slope, so rise over run. So rise over run times the run, the delta x, is going to give you the rise in the right triangle. I hope that that part makes sense. And then the hypotenuse of the triangles are the pieces that we're going to add to get the arc length, the total length of this curve. So using Pythagorean theorem, you'd be computing square root of delta x squared plus dy over dx squared delta x squared. And we have delta x squared inside of the square root that we can pull out. And then you can kind of see that from that formula, in the limit, that's going to turn into square root of 1 plus the derivative squared times dx. And we're going to integrate that from a to b to get the total arc length of this curve. Okay, so that's how the formula was derived in Calculus 2 class. But actually, in the Calc 3 setting, when you're doing parametric equation or vector function, the formula for arc length, I think it makes more sense. You don't have to go through this mental gymnastics with Pythagorean theorem and looking at that infinitesimal rise and run. The formula for the vector function version is just this square root of the derivative in x direction squared plus derivative in y direction squared. Or that expression already has another meaning. It's the magnitude of the velocity. So it's the speed. So if you integrate over speed from time equals to alpha to time equals to beta, that gives you the distance traveled, which is the arc length. So I think the formula is easier to memorize because it has a kind of more intuitive meaning, right? It's the magnitude of the velocity. So it's the speed at which the particle is traveling. And then if you integrate over the speed, you get the distance traveled. So I think in that sense, it's a simpler formula. It makes more sense, I feel like. So let's take this out on a test run. And another benefit is that going from 2 dimension to 3 dimension is pretty obvious what to do, right? So instead, this is a 2-dimensional version of the vector function, but if we have another third component, we'll just add dz dt squared inside the square root, and we'll get our formula. All right, so let's compute the length of a helix. So we have some formula. This is in parametric form. To compute it, let's take the derivative of each piece. And the derivative of the z component is just a constant h over 2 pi. So just to kind of remind you, h is the gap between each winding of the helix. And r is the radius from the z-axis to the helix curve itself. Okay, once I have those, I square them and add them up. And make sure to add the z components as well. Okay, and let's compute the length of helix in just one wraparound, so from 0 to 2 pi. Okay, so the inside of the square root simplifies quite a bit. If you factor out the r squared from the first two terms, sine squared plus cosine squared is always equal to 1. Okay, and what's left is a constant. It doesn't depend on t at all. So this constant, I could just pull that outside of the integral sign, and if we integrate constant 1 from 0 to 2 pi, I'm just going to get 2 pi. So this is the constant part. And I just multiply that with 2 pi, and we get the length of the helix. So that's how we can compute the length of the helix. Since this one was kind of a little bit too straightforward, we just got a constant integral. So maybe a slightly more complex version of a very similar thing. Maybe I'll do a two-dimensional spiral. So let's compute that. So to take the derivative here, I have to use the product rule. Derivative of cosine is negative sine, so I get that. And y prime is going to be very similar. Like that. If I square them, let's see, I think I'm going to factor out e to the t and then square them separately because it's every term is going to have that. And then what's left is cosine t minus sine t. So if I square that, I get cosine squared minus the cross terms plus sine squared. And I'm going to get very much a similar expression for the square of the y derivative. Okay. All right. So this is going to simplify quite a bit when we add it to each other. In fact, even before we added, cosine squared plus sine squared is going to be 1. And sine squared plus cosine squared is going to be 1. And again, let's integrate just from 0 to 2 pi here. So inside of the square root, I have e to the 2t in front of everything. And here the x prime part becomes 1 minus 2 cosine t sine t. And the square of the y prime is going to be 1 plus 2 cosine t sine t. And the cross term part cancels out very nicely. So we're just left with 2 times e to the 2t. Square root of 2, I can pull out. And square root of e to the 2t is just going to be e to the t. Okay, so all we have to do now is find the antiderivative and plug in 2 pi and 0. And e to the 0 is just 1. So there's that one. Okay, I think I want to end the video here. And in the next video, we're going to talk about some other features of curves that we might be interested in, like curvature.